In this next segment, we're going to look at vascular resistance and how this influences the distribution of blood flow. This next table here shows a variety of the major organs in the body, everything from the GI system to kidneys, brain, heart, skeletal muscle, and so on, and shows the relative amount of blood flow it gets in mils per minute. I don't want you to memorize these numbers. Really, the point of this slide is simply to show that the blood flow to these different tissues is not equal. And this is because the vascular resistance to blood flow is not equal among these organs, and they are adjusted appropriately based on the metabolic demand. And so it's not necessarily even based on the size. So some structures that are not very large, like the heart or the brain, relative to other structures of the body, receive a disproportionate amount because the metabolic activity is so high. Again, don't need to memorize those numbers. I just want to put that in there to show you how unevenly distributed the flow is. So blood flow, let's look at the physics of this a little bit. So blood flows from a region of high pressure to a region of low pressure, and the rate of the flow is dependent then on the magnitude of that difference. So this diagram here shows a very crude description of the vasculature in the body. So we have the heart over here with the right and atrium and ventricle, and then the left atrium and ventricle, and then this represents the arteries, and this represents the veins, then coming back into the right side of the heart. The highest pressure is over here on the left side, leaving the left ventricle. It varies, as you'll see in more details later, between systolic and diastolic pressure, but the mean arterial pressure is about 100 millimeters of mercury or so. The pressure over on the right atrium then that receives blood from the vena cava has extremely low pressure. It's about 0. So the pressure difference, delta P, the pressure difference between the left ventricle and the right atrium is about 100 millimeters of mercury. So this is, in a sense, the driving force then for moving that blood. So if we look at blood flow and the things that control it, so that pressure difference is one of it. But another important part is the resistance to the blood flow within the vessels themselves. And so the blood flow goes up as the pressure gradient goes up, but the blood flow goes down if the resistance goes up. So again, delta P is just simply characterizing the difference in pressure between two ends of a tube. Say, for example, the left ventricle versus the right atrium. So resistance is a little bit more complicated. A variety of different components contribute to resistance. One is L, the length of the vessel. The other is this symbol called eta. This is the viscosity of the blood, how thick the blood is. Oil, for example, is thicker than water, has a greater viscosity. Grease has a greater viscosity than oil. This is what is meant by that term. And then R is the radius, the diameter, in a sense, of the blood vessel. So this is then described mathematically by something called Poisson's law. And it looks a little bit complicated here initially, but it's actually not very complex. And let's describe this in a little bit more detail. So blood flow is going to be equal to the differences in the pressure, delta P, times the radius to the fourth power. This is a very important point here we'll come back to. Times pi, well, that's a constant, divided by eta, viscosity, times the length, times, well, 8, another constant. So, well, vessel length doesn't really change in any significant way, certainly not moment by moment. Vessel length can change over the long term with exercise. So if you go from being very inactive to being very active, you will sprout new blood vessels and increase blood vessel length as a consequence, but that's not a short-term process. That's not something that happens moment by moment. Also, moment by moment, blood viscosity doesn't really change either. No, it can change. Blood viscosity goes up if you get dehydrated. That will increase your viscosity. And with a condition called polycythemia, this is an overproduction of red blood cells. Again, not all that common, but this also increases blood viscosity. So it's mean arterial blood pressure, this P right here, and vessel radius, that's the most important part of regulating blood flow because, well, the rest of these things just don't change very much. Blood pressure changes, and also then the resistance, the radius of the blood vessels can change quite dynamically. So pressure can change very dynamically, and radius the blood vessels can change quite dynamically, and this can change then blood flow tremendously, redirect flow from one tissue to another tissue. So let's take a look at this issue, this effective radius. So here is the blood flow coming in, and this blood vessel here then branches into two smaller vessels. It has a radius of 1, and so it has a resistance of R, and the blood flow is F. And these two are equal to each other because they both have the same radius. In this one here, we're going to double the radius. And if you notice, we double the radius here, the resistance drops to 1/16 because the resistance is proportional to the 4th power of the radius. So it's 2 times 2 times 2 times 2. So we end up with 1/16 of the resistance. And as a consequence, the blood flow goes up by 16-fold. It's a huge, huge change for a relatively small physiological compensation here. Same thing here. This one is going to decrease the radius by 1/2 from here. And as a consequence, the resistance goes up 16 times over the resistance in this particular condition here. And as a consequence, the blood flow is 1/16 in this blood vessel compared to this blood vessel. So changes in blood vessel radius, diameter, has a tremendous impact on blood flow. Okay? Now, the point of this slide is that blood flow to the various organs of the body, the liver, kidney, for example, let's say skin, GI, over here, these are blood vessels that are in parallel to each other. So a change in resistance in one pathway doesn't change the resistance in another pathway, but change in resistance in one pathway, say the skin here, but let's say we're going to increase the resistance tremendously, will shunt the blood then to the other pathways. So this is what happens, for example, in a fight or flight response. If you vasoconstrict blood vessels in the skin, the GI system, this shunts blood to the skeletal muscles and to the heart and to the brain. Also, vasodilation in a large organ like skin, for example, can make a very dramatic decrease in total peripheral resistance. That is the resistance of the whole system. And typically this is caught then by vasoconstriction in some other part of the body and or an increase in cardiac output so that you don't have an unphysiological drop in blood pressure. So let's take a look at the regulation here of this blood flow. So there's extrinsic regulation. What's extrinsic about this is controlled by autonomic and endocrine regulation of blood flow. Sympathetic nervous system. So there's a huge increase in peripheral resistance that happens with the release of norepinephrine. They're going to have effect on the smooth muscle of the arterioles via alpha receptors, alpha-1 receptors, and cause vasoconstriction. It's also going to cause a big increase in cardiac output. Not only are you going to get an increase in heart rate, but you're also going to get an increase in stroke volume via an increase in contractility. Now, epinephrine has a somewhat different effect because epinephrine, as I reminded you some time back, has a higher affinity for beta receptors than it does for alpha receptors. And so beta receptors cause vasodilation. Alpha receptors cause vasoconstriction. So in a fight or flight response, what happens is you're dumping out a whole bunch of epinephrine, adrenaline, from the adrenal glands. And so you get vasoconstriction in some parts of the body. That is, the skin, for example, has mostly alpha receptors and very little beta receptors. And so it vasoconstricts. Conversely, even though you have both alpha receptors and beta receptors in major muscles, the epinephrine is going to override the effect of the norepinephrine. It's going to bind to those beta receptors and cause vasodilation. So in a fight or flight response, you vasoconstrict in some parts of the body based on the type of receptors they have, alpha, so skin and viscera constrict, and you vasodilate in other parts of the body, major muscles, and this then helps to prepare you for that fight or flight response. So here it shows this extrinsic control of vascular resistance and all the different kinds of things that alpha receptors and beta receptors and parasympathetic and other kinds of things can do. I'm just going to leave this table in here for your reference, and we'll continue to talk about these in other sections. So then let's look at the other part of the autonomic nervous system, the parasympathetic nerves. And so they release acetylcholine. Acetylcholine is largely vasodilatory. It really doesn't have a very big effect because, well, it doesn't have very many tissues that it innervates. So digestive tract, external genitalia, salivary glands, it does cause vasodilation in those structures, but they don't make up a huge part of the body, so they don't have a huge effect on overall total peripheral resistance because it's relatively limited about the parts of the body that are affected by this. So then let's look at paracrine regulation. So this is paracrine, if you remember, this is molecules released by one tissue, then locally affecting another tissue. And so, for example, the tunica interna, this is the endothelial layer of blood vessels. This can release then regulatory molecules that influence the smooth muscle of those blood vessels, the tunica media. And so some of them are relaxing, cause relaxation of that smooth muscle, bradykinin, nitric oxide, one of the prostaglandins. These produce vasodilation. Another one, endothelin 1, is a powerful vasoconstrictor. And so this will increase total peripheral resistance. And these other ones here, because of causing relaxation of smooth muscles, will drop total peripheral resistance. So these are the paracrine regulators. But then there's also something referred to as intrinsic control. What's intrinsic compared to extrinsic? Extrinsic is hormonal or the autonomic nervous system. Intrinsic is intrinsic to that tissue itself, that structure itself. So some organs, and we'll get into these a little bit more detail in other parts of the course here, like the brain, for example, or the kidney, have their own mechanisms to modify blood flow. The idea here is to maintain blood flow relatively constant in the face of changing pressures. And so this is referred to as autoregulation. And this comes in two flavors, actually. One is myogenic control. And these blood vessels, not all in other parts of the bodies, but in these particular structures, brain and kidney, for example, what happens is when they see a elevated blood pressure, which would increase blood flow, what they do is they reflexively constrict. So that smooth muscle then will contract and reduce the radius of those blood vessels and bring that blood flow back down to normal in the face of a raised pressure. If the pressure goes the other way, it drops, those blood vessels will reflexively relax. That smooth muscle relaxes and the diameter of those blood vessels increase, and this helps them to recover blood flow to its normal level in the face of a lowered pressure. So that's myogenic, myo as in muscle. And then there's metabolic regulation as well. This has a variety of different components to it, but they should all make pretty good sense. So the idea here is to look at what is happening metabolically in active tissues. And so, well, oxygen concentration locally goes down because those tissues are sucking up that oxygen for oxidative phosphorylation. That drop in oxygen causes local vasodilation. Likewise, when the metabolic activity increases, more carbon dioxide via the citric acid cycle, more carbon dioxide is being produced, and that causes local vasodilation as well, indicating this tissue is hyperactive. When the tissue is active, it also drops the pH, and this is due to the increase in CO2. We'll talk about that chemistry here a little bit later. But also, if you recall, if you don't have enough oxygen around because you're depleting it because the tissue is highly active, some of that glucose going through glycolysis then will not make it into the mitochondria and instead takes this side pathway to produce lactic acid, and that drops the pH as well. That lowering of the pH indicates that tissue is metabolically active and causes vasodilation and increases blood flow. As well, there will be a release of potassium from intracellular stores into the extracellular space, indicating metabolic activity. And then other paracrine signals, some of the ones we've talked about before, nitric oxide, for example, are released as well. And this causes local vasodilation as well. And then there's something called reactive and active hyperemia. Hyperemia simply means increases in blood flow. What reactive hyperemia is if you constrict blood vessels. So let's say you pinch off your wrist and block the blood flow to your hand for a minute or two. What's going to happen is your your venous blood supply cannot rinse away the metabolic waste products that are building up as a consequence of the metabolic activity of your hand. And so as soon as you then unclamp it and you resume that blood flow, you'll get this large increase in vasodilation and blood flow, and this will cause something that causes, then you'll get this little reddish color to the skin. That's the reactive hyperemia aspect of this. Active hyperemia is simply an increase in metabolic demand then causing an increase in blood flow and then producing some reddish skin. So for example, if you were to take a weight and you were to curl that many times in a row, you'll warm up and notice that your bicep will get a little pink because of this increase in blood flow, because of that increased metabolic demand and the need then to deliver more blood to that region.